All right, this is test review worksheet number 2 for chapter 5 on logs and exponential functions. So the back page here for number 2, find the derivative, find dy dx for our equation, natural log of xy squared is equal to y squared minus 3x. Now here, I'm going to, because this is within the natural log expression, I'm going to try and expand this a little bit more. We know that ln of ab can be expanded to be ln of a plus ln of b. So I'm going to rewrite this as ln of x plus 2 ln of y is equal to y squared minus 3x. That way we can avoid product rule. But here you see that we have to use implicit differentiation. We have the y's mixed in with the x's. This is not a function that is solved as y equals. So now we have separate terms, so we can just find the derivative for each term, and remember that each time we come across y's derivative, we have to remember to attach a dy dx. So ln of x becomes 1 over x. 2 is a coefficient, so that stays. ln of y becomes 1 over y, right? Ln of the derivative for ln of u is u prime over u. So ln of y becomes 1 over y. Involve y's derivative, so dy dx is equal to y squared becomes 2y dy dx. 3x becomes 3. So now we can try and get dy dx by itself. So let's move dy dx to the left side. All the terms that involve dy dx, move that to the left. Everything else to the right. And then divide both sides by 2 over y minus 2y. We have a complex fraction that results. So the way that we can clean this up a little bit more is if we can distribute everything through with the portion that is causing this complex fraction to occur. So there's an x in the denominator here, there's a y in the denominator here. If I multiply everything through by x and y, then it will cancel out and clean these denominators up to be a little bit better. So xy, distribute the xy through to negative 3, we get negative 3xy. Distribute the xy through to the negative 1 over x. The x's will cancel out, but the y will be left over. Distribute the xy through. The y's will cancel out, leaving us with x squared, leaving us with, sorry, this is a 2 here, not an x. So distribute the xy through, y's cancel out, 2 times x is 2x. And then multiply the xy with the 2y, we get 4xy squared. Okay, so this is a little bit cleaner form of our derivative function, the derivative equation. Okay, so number 3, given our function natural log of 4 minus x squared, find the domain of our function. So the domain is going to occur where the natural log, anything inside a natural log function has to be a positive value. We can't have any negative values. And the way that we can test that is if we can find critical points that sits in this argument of natural log, we can then test each interval to determine where the graph exists. So 4 minus x squared, if we set that equal to 0, we're going to have 2 critical points, one at 2 and one at negative 2. So we put those on the sign line. And if I plug negative 3 in for this expression, I get 4 minus 3 squared, which is a negative value. So negative in this portion between negative 2 and 2. If I choose 0, I get natural log of 4, which is positive. And if I plug in 3, I'll get another negative. So we know natural log can't exist in negative regions. So this natural log graph will only exist between negative 2 and 2 in the open interval of negative 2 and 2. So that's our domain. For b, find the range of f of x. So if we want to find the range, we know that the graph is going to be increasing up until natural log of 4, and it's going to start decreasing again. So this will become more apparent once we look at the behavior of the graph in terms of slope and relative max or relative min. So we'll come back to this one. For C, find the intercepts for f of x. So to find intercepts of f of x, we're going to set our function equal to 0, figure out intercepts occur where y is 0, so set that equal to 0. Now, once we set this equal to 0, I can think of this in terms of log base e. So log base e of 4 minus x squared equals 0. Convert this to exponential form. E to the 0 equals 4 minus x squared. Anything raised to the 0 is 1, so 1 equals 4 minus x squared. Subtract 4 from both sides. Negative 3 equals negative x squared. Divide both sides by 3. Take the square root, so I get x equals plus or minus root 3. Right. So my x-intercepts occur at plus or minus root 3. To find the y-intercept, we can simply replace the x with 0 and solve for y. So if I replace x with 0, I'll get natural log of 4 minus 0, which is 4. So natural log of 4 will be my y-intercept. Determine the asymptotes. Well, asymptotes occur within the argument that will cause natural log to be 0. So if negative 2 and 2 will be those values that cause this expression to turn into 0. So there's our vertical asymptote. For e, find f prime. So to find f prime of x, we can simply apply the rule for a natural log of u. So that which is u prime over u. U prime is negative 2x over the u value. So u prime over u, negative 2x over 4 minus x squared. To find f double prime, we can go through quotient rule from f prime to get to f double prime. So f prime g minus f g prime all over g squared. So here we have f prime g minus f, which is negative 2x, times g prime. So 4 minus x squared becomes negative 2x, all over the denominator squared. We can try to clean this up a bit, distribute, and get rid of the parentheses. We're left with negative 8 plus 2x squared minus 4x squared, which reduces to be negative 8 minus 2x squared over 4 minus x squared quantity squared. Factor out the negative 2, and this is probably as far as we can go in terms of getting this second derivative function to allow us to find critical points easier. Okay, and we'll have to do that a little bit later on. So for g, find the intervals where the graph is increasing and decreasing. So remember, critical points can come from critical points for max and min can come from both numerator and denominator. So numerator will give us a critical point of 0. We set numerator equal to 0, we get x equals 0. Set the denominator equal to 0, we get 2 and negative 2. So we'll put those points here. We're not going to test anything to the left of negative 2 and 2 because these are asymptotes, and we know from our domain is only from negative 2 to 2. So we only need to test two regions here. If I plug negative 1 into the derivative, remember we're trying to determine the behavior of the slope of the graph. So plug negative 1 into the derivative function. So I'll get a positive over a positive, which is positive. If I plug in a positive 1, I'll get a negative over a positive, which is negative. So I know that my graph is going to be increasing, hit a maximum at 0, and then decrease. For part H, determine the intervals of concave up and concave down. So here, there's no critical points from numerator, because if we try to set 4 plus x squared equal to 0, we're going to get an imaginary number. If I set the denominator equal to 0, then I'm only going to get those. I'm only going to get the vertical asymptotes, which is at negative 2 and 2. So really, we'll need to test this region between negative 2 and 2. If I plug 0 into the second derivative, I'll get negative times positive over a positive, which is a negative. So this portion means that the graph will be concave down. So we know our graph is concave down between negative 2 and 2 because f double prime is negative. And also, forgot to mention, the relative maximum is at 0, natural log of 4. Plug 0 back into the original function to get the relative max. And our because statement is f prime changes from positive to negative slope. Okay, when we sketch our graph, we know the vertical asymptotes is at negative 2 and 2. We know that our graph is going to be increasing between negative 2 and 0, hit a maximum and decrease while maintaining concave down the whole way through. So here is our basic sketch of the graph. And then based off of this, we can justify the range a little bit better. So here you can see that the graph goes all the way down to negative infinity, but it goes as high as natural log of 4. So that is, again, our range from negative infinity, y value of negative infinity, to a y value max of natural log of 4.